In this video lecture, we will discuss the Gauss law. So this Gauss law is related with the flux. And we know that flux is something, or this is a surface and something passing through this surface. We will call it flux. And there may be the electric field lines or magnetic field lines. So here in the Gauss law, we deal with the electric flux. So here we will consider any closed surface, and we will consider here the charge Q is enclosed in this surface. So the amount of this Gauss law states that total electric displacement or electric flux through any closed surface surrounding charge Q is equal to the amount of charge enclosed so this is the Gauss law. So here we have considered the charge is Q is located in this in a homogeneous isotropic medium whose dielectric constant is epsilon, that we consider charge Q is enclosed in a homogeneous isotropic medium whose dielectric constant is epsilon. Now here we will consider a small area element. Say this is dA is the area element, and this is electric displacement density vector, and normal to this surface this vector is say n, and this vector is say d, electric displacement density vector, and this makes an angle of theta. And say r is the distance between this position of the charge, in between the position of charge and this area element. So the electric field strength at the surface of this area element, we can write this is E is equal to Q by 4 pi epsilon naught r square, and r is the position vector. And we know that electric displacement density is given by d. D is equal to epsilon naught E, and it comes out to be q by 4 pi r square, r position vector. And now we want to find what is the total flux through this small area element dA, that electric flux or electric displacement oblique electric flux through area element dA is, we can represent it with d phi is equal to d into dA cos of theta. Now here theta is angle between this normal to this area element and this displacement element, electric displacement density vector, and this dA this is this area vector, this black color area element dA is the projection of dA normal to the this radius vector. So this is the projection of dA normal to the this radius vector r, or with respect to this position vector. Here we can this represent the direction. So this is the and if we this is the angle which we call the solid angle here, and we denote it with symbol d omega. So by the definition of solid angle for this figure, because this is the projection of the dA normal to this radius vector. So by the definition solid angle, we can write this is dA cos of theta upon r square. So in order to find the total flux through this closed surface, that in order to find the value of total flux or total flux, that is electric displacement that is electric displacement or electric flux total electric flux is given by taking the closed surface integral, that d dA cos theta d phi. Say this is relation number 1, this is relation number 2. Now by using this definition of solid angle, we can substitute the value of from equation using equation 1. We can write dA cos theta is equal to r square cos of theta. So we'll use this dA cos theta in equation 2, and this total flux we can write this is phi d r square, this solid angle d solid angle, and we know that the value of, we substitute the value of t from here. In this relation, so the d is q upon 4 pi epsilon naught r square q by 4 pi r square. This is basically surface integral. We can write here as for closed surface integral into r square d omega. So q is constant, 4 is constant, pi is constant. We can write it q by 4 pi. This is a closed surface d omega. So we know that the value of this integral, it is equal to 4 pi. So by substituting this value in this equation number 2, no, this is equation number 3, total flux comes out to be q by 4 pi into, here we have epsilon also, four pi, and that will get cancelled. So this comes out to be equal to q. So total flux comes out to be equal to q.